Okay, welcome back to my channel. Today we're going to be talking about stability of the atmosphere, and this is connected to a previous video that we did on lapse rate. Now, we can describe weather conditions as being stable and unstable. Stable weather conditions refer to weather conditions that are dominated by calm conditions, where situation is calm or there might be light winds, if any. The sky is clear and it is bright and sunny. Under these conditions, it is ideal to go for a picnic, to go for a walk, to go hiking, or you can even go to the beach. Stable weather condition occurs when a rising parcel of air is cooling faster than the surrounding air. And if it gets colder, which also means that it would be denser, then it will sink back to its original position. Now, this diagram that we're looking at is a temperature height diagram. And notice it shows adiabatic lapse rate, the two types of adiabatic lapse rate, the DALR and the SALR, along with the environmental lapse rate. Now, because temperature is increasing the further you go to the right, what this means is that this is showing that the surrounding atmosphere, which is represented by the ELR, is warmer than the rising parcel of air, which is represented by the DALR and the SALR. Now, because it is warmer, because the surrounding atmosphere is warmer, the pocket of air is colder, then we are expecting that that cold air will sink back to its original position. Because if it's colder, it's also going to be heavier. If there was a rock at the bottom of a river and you went up and you pulled up the rock to a mid-level in that river and you let go of that rock, you are expecting that rock to fall to the bottom of the river once more just because it is heavier. It's the same thing that is happening in this situation. The pocket of air, because it is colder than the surrounding air, is going to fall back to its original position. And therefore, this kind of situation is where air rising is not being promoted. It is being impeded by the higher temperature of the surrounding air. All right, and we know that we associate sinking with stable weather conditions. So again, this is another diagram, again showing the stable weather condition. Again, notice that the surrounding air represented by the ELR is to the right. Again, it shows that it is warmer than the rising pocket of air. All right. Now, stable weather condition will definitely occur in a situation that we call temperature inversion. Temperature inversion is where atmospheric condition is opposite of what we normally expect to happen. What we normally expect to happen is for the air to get colder and colder with height. In the case of temperature inversion, it's a case where we have a warmer layer of air above a colder layer of air. All right. And because we have a warmer layer of air at the top, it is going to be difficult for an air pocket to actually rise through that warmer layer of air. So under that condition, air tends to sink back, giving rise to stable weather conditions. All right, so this diagram is comparing normal conditions with the condition where there is an inversion. So under normal condition, we expect the warmer air to be closer to the surface, and then it gets colder and colder as we move up. Under that condition, it is easier for air to rise. But when we have a warm layer of air, as shown in the second diagram, acting like a seal or a cap, it makes it difficult for a rising pocket of air to continue to rise. And therefore, under that condition, air will sink back to its original position and therefore will give rise to stable weather conditions. Now, what are some of the conditions under which stable weather conditions in terms of temperature inversions will occur? Temperature inversions may occur during a depression where warmer air overrides colder air. It may occur when warm wind blows over cooler air below. It may also occur where we have radiation cooling. So during the evening where the air, the surface is losing its heat and cools down, it may get colder than the air above it. Again, under that condition, we would have temperature inversion. So that was stable weather condition. We also have a condition known as unstable weather condition. And we can talk about absolute unstable weather condition and conditional unstable weather conditions. Unstable weather conditions, or we would say instability, refers to weather that is dominated by overcast conditions associated with strong winds and heavy rains. Under these conditions, it is best to stay inside. And if you do have to go outside, it is best for you to dress warm and take your umbrella with you when you're driving on the road. It's best for you to be very cautious, all right? Because these conditions are usually associated with hazards. All right, so the picture that we're looking at is representing an unstable weather condition. There are lots of clouds, we have heavy rainfall, we have strong winds, we have lightning, and so persons are dressed warmly, and they have their umbrella with them. All right. Unstable weather conditions occur when a rising parcel of air is cooling slower than the surrounding air, so that it remains warmer and lighter than the surrounding air. And because it is warmer and especially lighter, it is going to rise. And oftentimes it rises to the point where condensation takes place, clouds form, which eventually result in precipitation. So this temperature height diagram is showing instability. Notice that in this case, the ELR is to the left of the DALR and the SALR. What that means is that it is the ELR is colder than the DALR and the SALR. And under that condition, the rising pocket will be able to continue to rise. All right, again, this is another diagram showing unstable weather conditions. Notice, same thing, it is showing the ELR to the left. And remember, left represents colder conditions. So because the DALR and the SALR, which represents the rising pocket, is to the right, it means that they are warmer than the surrounding air, and that will cause the air to rise, cool, condense, and give rise to precipitation, etc. We also have a situation that we call conditional instability. Now, when it comes on to absolute instability occurs only in situation where the air close to the surface is very hot. And because it is very hot, it has enough heat to keep it rising to very high levels where condensation can take place. In the case of conditional instability, I want you to note that it's going to be different. In the case of conditional instability, the unsaturated air is going to be stable, and the saturated air is going to be unstable. In other words, the rising pocket of air, before it gets to its condensation level, has all the potential to sink back because it is colder than the surrounding air. But because some other factor, a forcing mechanism, causes it to continue to rise, it is not rising because it is warmer, it's rising because some other factor is at work. It rises to the point where it gets to its condensation level. And remember, when condensation is reached, the water vapor, in order for the water vapor to change to liquid, it has to release some of its heat. When it releases that energy, it releases it into the air pocket, which in turn gets warmer. And because it gets warmer, it's going to cool more slowly. And it is because it starts to cool more slowly that the conditions at that point will become unstable. So conditional instability is where the atmosphere is stable for unsaturated air and unstable for saturated air. If the air can be forced to reach condensation level, either by ascent over hills, so that is one way in which the air may be forced to rise, even if it's not warm. If the air comes across a relief barrier like a hill or a mountain, in order for it to pass that relief barrier, it will have to rise. Rising may also result where two air masses meet and the warmer air mass is forced to rise over the colder air mass. All right. So under that condition, air may rise and reach its dew point or condensation level, so that the situation will change after that. So let's look at our temperature height diagram. Notice, let us examine the DALR, which is representing the unsaturated air. That is the air that has not yet reached condensation level. Notice the DALR is to the left of the ELR. What that means is that at that point, the pocket of air is colder than the surrounding air. If it's colder, it means that it's heavier, and because it's heavier, then we are expecting it to sink back to its original position. But that doesn't happen. Something is at work. Some other factor is at work. And that other factor keeps the air rising so that it gets to its condensation level. When the condensation level is reached, remember what happens? I will repeat. Water vapor is now going to be changed into liquid. In order for that to happen, it needs to lose some of its energy. So it releases that energy into the air pocket. The air pocket warms up, and because it has warmed up, then it's now going to be cooling at a slower rate. At that point, conditions become unstable. So eventually, if you notice, there's a point where we see that the SALR crosses the ELR and is now to the right of the ELR. And at that point, it means that it's free to rise. All right, so this is conditional instability. All right, so before I end, I just want to show you another diagram. Again, it's a temperature height diagram. I want to show you how the stability of the atmosphere is directly related to the cloud formation. So in this diagram, we are seeing a situation where conditions are unstable. How do we know that it is unstable? Because we notice that the ELR is to the left Or we could say it a different way, the surrounding atmosphere is the surrounding atmosphere is cooler than the rising pocket of air. So our DALR is to the right. Then we see condensation. Notice the condensation level. Condensation level is where condensation obviously begins. Water vapor changes into liquid. And as long as we have condensation nuclei, which are the various dust particles that exist in the air, then our water vapor is going to condense on those surfaces and our clouds will begin to form. Now, our clouds will continue to develop vertically as long as conditions remain unstable. Notice, however, that close to where we are at about 5 kilometers, notice that the cloud development stops around that level. And that's because there's a little switch taking place right there. Notice at that point, we see that the ELR and the ALR, in this case, the SALR, are now at the same point. It means that they have the same temperature and therefore the same density. So at that point, after that, at least, we're going to find that the situation is going to be changed and the air is now going to become stable. So no further cloud development will continue. So if you get a question like this in your exam, you should be able to explain where the clouds begin, where it ends, and exactly why it begins where it does and why it ends where it does. All right. So I will stop here. I do hope that you learned something. If you have any questions, you could leave them in the comment section. All right. In the meantime, if you have not yet subscribed, please subscribe to my channel and support me. Please like and please share with someone else who you know that this information will benefit. Thank you, as always, for watching or for listening.